Greetings everyone, and welcome back to your second of two lectures on Chapter 10, or the population of stars in our universe. If you remember from last time, we had already determined most of the major characteristics of stars. The only one that was missing, of course, is mass, and that one is more tricky. Fortunately, the answer lies in something that we call multiple star systems. Most of them are binary star systems, right, where you have like one star and another star and they're orbiting around each other. Sometimes there are what we call ternary or trinary star systems, where you have two that are kind of in close orbit and there's a third one that's kind of orbiting around the both of them. But as it turns out, more than half, but probably as high as maybe 80% even of star systems are multiple star systems. They're usually binary, but some like Alpha Centauri are actually the ternary or trinary star systems. There's lots. Now because binary star systems are common, it makes it really, really easy for us to find them out in the universe, right? Two stars orbiting a common center of mass is the most common, but there are enough everywhere that we can really kind of put all of this theory to the test very easily. For starters, there are several different kinds of binary star systems. There are visual binaries. So there's visual binaries. And those are stars where we can actually see both of the stars. You can visually resolve them. Like, that's a star and that's a star. Like, I think the image that we have in today's image bank is Alpha Centauri A and B. And they have a visible resolution of something like 1.5 arc seconds. And so we can very visibly see that because they're close to us, we can see how far apart they are and actually see that there are two stars there. There are some other ones, and any other ones that you can actually see the stars, those are called visual binaries. There are also what we call spectroscopic binaries. And those are different from visual binaries in that we can only actually tell that there is more than one star there because we get a repeating Doppler shift pattern from the light that these stars give off, that they actually make it to us. And then of course there's this other funny thing called an eclipsing binary. And these ones are actually kind of interesting. Imagine, if you will, that you have two stars that are orbiting each other. You have like, one big one and like one small one or whatever. Okay, now if you're looking at the light from this star system, right? Let's say that this is like a scale of luminosity or brightness or whatever. It's going to kind of just be the same unless this star goes in front. Now, what's going to happen when this star goes in front of this other star? Well, this small star is going to block out some of the light from this star, right? But we're still going to be able to see the light from this star. And so while this star is in front of this star, it's going to dip a little bit. And when it comes out the other side, of course, it'll go back to normal. But then when this star goes behind this star, its light is going to get blocked out completely, right? We won't see it at all. So it's going to dim even more. And then it'll come back around, and then it'll go in front, and it'll dim again for a little while as it's passing. And then it'll go behind, and it'll dip a lot again, and so on, right? We'll get this repeating kind of pattern. And that's what we call an eclipsing binary, because one of the stars occults or eclipses the other. Okay. Now that we know the various types of binary stars and what it is actually we're looking at when we're looking out into the universe, we can use a couple of straightforward physics tricks, analyses, techniques, tools, whatever you want to call them, in order to determine the masses of stars in a binary system. We can start, of course, by observing the Doppler shifts of the two companion stars. And there's a nice image, I think it's the second image in our image bank. If you kind of look at, this would be like a reference point. If there was just some star that wasn't moving away from us or towards us, it would have zero Doppler shift, right? But then, let's say that now there's two stars, right, and they're kind of pulling each other around. Part of the time, one of those stars is going to be coming towards us, the other one's going to be going away from us, and so on. Now, let's say that one star has a certain amount of Doppler shift, right? So it moves towards us and then away from us, right? We get a blue shift, red shift, blue shift, red shift, and then the pattern will repeat, right? But the other companion star, if it has its own spectral signature, right, but its Doppler shift is much, much more noticeable, what can we tell about this system? Well, obviously, the one that has the greater Doppler shift is moving more, right? If we recall, Newton's third law says that forces always occur in pairs equal in magnitude and opposite in direction. And these two are exerting the same gravitational force on each other, right? So we're talking about the same force, same magnitude, opposite attractive directions. And so if one of these stars moves way more, what's happening? Well, that means the star that moves way more has less mass, right? It's being accelerated with the same force, but because it's less massive, it's moving way more, right? And then the other star has more mass because it's moving less, right? Therefore, a star with, say, half the mass of the other star in the presence of an equal force with identical magnitude will accelerate twice as much. So, essentially, from the ratio of the two Doppler shifts, we can tell which star is moving faster, right? Therefore, which star is also farther away from their common center of mass, but we won't worry about that. But also, what the ratio of the masses is, right? Because force equals mass times acceleration. Now the force that they're both going to feel is the same, so the one that accelerates more has less mass. Pretty straightforward, right? Okay. Also, we can kind of look at how long it takes for these two things to orbit each other, right? Remember, we called this the orbital period, T. And from Kepler's third law, we have a relationship. So we can tell immediately how far away these objects are. That's not an issue. And we can tell by the repeating Doppler shift pattern what their orbital period is, right? However, what I didn't tell you about Kepler's third law, when we went over this before, is that this equation is simplified. Now, I already talked about how it only works if you use the right units, right? You also have to say period in Earth years and semi-major axis in astronomical units, right? Average distance has to be in average distances from the Earth to the Sun in order for this relationship to work. And one of the things that's normally in here, in this equation, is the sum of the two masses, right? The mass of this star, star 1, and the mass of this star, star 2, right? You call this like M1 and M2 or something like that, right? And those are normally in this equation somewhere, but we scale these units all appropriately so they just kind of become one and we don't worry about it. Okay? Now normally, in astrophysics, we don't write the equations this way. We usually use this funny quantity called the mean motion. And the mean angular motion is basically, we say that the mean motion, this triple equal sign, remember, defined to be, is 2 pi, or the total angle enclosed by an orbit, right? All the way around is 2 pi, divided by the angular period, or the orbital period, right? Now, if we scale this appropriately, of course, we can just kind of scale this 2 pi into the rest of the equation and just kind of remove it. And so essentially, that means that n is 1 over the orbital period. And so if we wanted to rewrite this equation, we can kind of write it, instead of t squared is equal to a cubed, we could say we divide both sides by t squared and multiply by n squared, right? So then we get 1 is equal to a squared, whoops, what do we just call it? N squared a cubed, because that's how we usually write it. Are you going to erase the board, Benjamin Ellis? But again, the thing that I told you about, we usually scale this 1, right? We usually scale this equation with the other variables in it. So this is actually the sum of the masses, m1 plus m2. Usually we write this as the Greek letter mu. Let me rewrite that. Usually we draw it this way, right? Mu is n squared a cubed. Sometimes we say n squared a cubed equals mu, whatever. But that's how we usually write this equation, right? Now, because we know the mean motion, or the orbital period, and because we know the semi-major axis, that means we know what the sum of the masses are, what the total mass of that star system is. And because we know what their Doppler shifts are, we know the ratio of the two masses, right? So we know like m1 plus m2 is equal to x, but we also know that m1 divided by m2 is equal to y. And we know what x and y are, and so we just have to do like a simple kind of substitution deal, and we can solve for these two masses, m1 and m2. And essentially, using this kind of analysis, we can basically solve for the mass of stars. Ta-da! Okay, that means we've basically nailed down all of the major characteristics of stars. And that has allowed us, essentially, to catalog the population of stars, especially those that are nearby us in our own galaxy in the Milky Way, right? And looking at a sample size as big as the Milky Way, we should be able to learn some things about the population of stars in the universe around us. We're going to see in the coming weeks that before stars become main sequence stars, when they're still proto-stars, and after what we call main sequence stars evolve into other celestial objects, they do not live in the major part of this catalog, right, that we call the main sequence. Objects like giants and supergiants and white dwarfs and so on, of course, are maybe some of the best examples of this. But if you look in today's image bank, we're looking at like the 7th or the 8th, the two Hertzsprung-Russell diagrams, what we usually just call the HR diagram. And that's not to be confused with human resources, of course. This is named for two people who worked on this a bunch. But the HR diagram basically is a plot of the population of stars all around us. And you'll notice that there is a couple of stars at the bottom. Those are like labeled white dwarfs, and then up at the top in the upper right-hand corner, there's giants and supergiants. But most of the stars on this diagram kind of go on this diagonal, right? there's a temperature scale at the bottom. This is temperature, and it increases this way and decreases this way. And then you have luminosity. Whoops. Luminosity or brightness, whatever you want to call it. And then that increases as we go up. And there's a little region down here where there are white dwarfs. There's a region kind of up here where there's giant stars and supergiants. But most stars appear on this huge diagonal kind of area, right? There's like supergiants up here somewhere. We call this part the main sequence. And cataloging stars into this main sequence has really helped us try to get a hold of the general characteristics of the population of stars around us. There are actually, if you look at the mass and the luminosity of the smallest stars and the largest stars, those are in like the like the 9th and 10th images. So the temperature and the luminosity for the really, really bright stars, the really blue ones, right? Obviously giant stars, because they have a larger surface area, are going to be bright. But some of the brightest stars in the universe are like on the main sequence and they're really, really blue in color, right? The hottest main sequence stars are blue. And the coldest main sequence stars are red. And of course, some blue stars are like as bright as some giant stars that are redder in color. And like I said, that's because they have their larger surface area, right? Giant stars are much, much bigger than normal main sequence stars. And of course, if we want to talk about the mass, for main sequence stars, the most massive stars are the hottest and brightest burning ones. Now the reason for that, of course, is the more massive a star is, the more material it has, the stronger the force of gravity, and the more pressure and temperature there's going to be in its core. And the hotter it is in the core, which is sort of the engine, if you'll forgive the crude comparison, but that's where all the heat gets generated, in the core of the star, where all the nuclear fusion is happening, right? Hydrogen gets fused into helium. And as a result of that happening, it's much, much hotter in the core of the star than it is anywhere else. And in a bigger, more massive star, it's going to be hotter in its core than it's going to be elsewhere in other stars, right? Obviously, our sun's core is not as hot as the core of, say, a blue star would be. Makes sense, right? So not only is there more temperature, which is going to be, leading to more nuclear reactions per unit time, also the cores are larger, and as a result they burn through their hydrogen fuel much more quickly. If you look at the lifespan, there's one of the two tables, the first one after the Hertzsprung-Russell diagrams, it shows you the lifespan of stars on the main sequence, and class O stars, the brightest, bluest, hottest ones, are only up to maybe 10 million years, sometimes as few as only 1 million years. And even though they have all of this crazy amount of matter in them, they've got so much intense pressure and temperature in their core that they burn through their hydrogen fuel in the core so quickly that it's gone in, maybe a million, maybe 10 million years. Whereas a star like our sun, if you look in the G row, right, our sun is mostly kind of yellow in color, even though the single brightest color is green. It's going to live about 10 billion years, or 10 giga years. That's what the capital G means, right? Like gigabytes on your hard drive. Most G-class stars live between 7 and 15 billion years. But class M stars, the lowest mass, coolest main sequence stars, can live over 50 billion years. Now, the universe is likely about 13.7 billion years old. And that means probably the red stars, the dim ones, that were first made just after the Big Bang, because they live so long, they're probably still around. So there are a bunch of the first population stars around from after the Big Bang. Okay, now as we started to populate this diagram, we noticed very quickly that about 90% of the stars that we found were in this part of the diagram. And so we can only conclude that stars must spend about 90% of their lifespan where they're bright enough to give off light, from heat and so on, so that they're visible. They have to spend 90% of their lifespan on the main sequence for 90% of the stars that we can see to appear there. So, 90% of stars that we can see live on the main sequence. Now, there are lots of correlations between these. Obviously, the hotter something is, the brighter it's going to be. But also, things can also be bright because of their size. There's definitely a correlation between color and temperature. Hotter stars are going to be bluer, colder stars are going to be redder, and then if we're talking about main sequence stars, colder stars live longer and hotter stars have shorter lifespans. But the mass, more massive stars are bluer, brighter, and hotter. Less massive stars are smaller, redder, and colder. Not to mention, bluer main sequence stars are larger than red main sequence stars. Red main sequence stars are small in comparison. If we want to talk about actual physical size, the class M star might only be like a sixth, or like maybe up to half the radius of the sun, and only has like maybe 5%, like a 20th of the sun's mass. But a blue star may have 10 or 15 solar radii, right? It'll be 10 to 15 times the size of the sun, and between 20 and 60 times its mass. Huge, enormous, right? So there's a big variation in between these huge, hot blue stars and these tiny little red ones. Now, obviously that means that not every star lives on the main sequence also, right? We have white dwarfs, and we have giants and supergiant stars. But if we look at the light given off by these stars, they do not look like the kind of main sequence light. They don't have those same absorption spectra features, because objects like white dwarfs and giant stars don't have atmospheres in the same way that main sequence stars do. And so we can instantly tell that if we're looking at the light from a white dwarf or a giant or a supergiant, that we're looking at light from a star that's not a main sequence star. And thus, if we look at the light from a main sequence star and we see those absorption features like we were talking about last time, we can use spectroscopic parallax in order to try to determine how far the star is from us, determine its absolute magnitude, and therefore its spectral class and all that other good stuff. Okay? Oh, by the way, down at the very bottom here, this temperature guide, right, which tells us that class O stars are the hottest, class M stars are the dimmest, whatever. There's an order. It's O, B, A, F, G, K, M. Goes in that order. Now before I talk a little bit more about that, we call it the spectral sequence. I just want to pose a question to all of you. Why is it that there are no green stars? It's a fair question, right? Isn't green in the middle? How come there's white stars in the middle instead of green stars? Is that just racist or what? Well, that's actually because starlight is light, right? It's not like paint. If you take paint, you're like subtracting the amount of light that gets reflected to your eye, right? You're blocking light out with paint. But with light sources, light adds to other light, right? And green is kind of like right in the middle of the visible part of the spectrum, right? So stars that are really, really bright in the green part, not just, having one single green wavelength that it's brightest in like we do. We're not that bright in some of the other shades of green, so we don't appear greener, so to speak. But stars that appear white have a lot of green, and they have just about as much red as they do blue, right? And so when you add up red, green, and blue, those are what you call your primary additive colors, right? When you add up all colors together, if you're talking about a light source, essentially you get the color white, like the whiteboard. And so because you're adding up all these colors, red, blue, green, violet, orange, all this stuff, because you're adding them all together, you get white. And that's why there's white stars kind of in the middle of this distribution. There are no green stars, even though they all give off green light, because they're all black body radiators. Okay, one last thing. This thing here, the spectral sequence, I want you to devise a mnemonic for remembering the spectral sequence. O-class stars, of course, are the hottest, so they're going to come first, and M are the dimmest, reddest, and coldest, and least massive, smallest in radius, all that stuff. So these are going to be at the end of the sequence. So I want you to come up with a mnemonic for remembering O, B, A, F, G, K, M. Okay? There will be an upload page for this, of course, and the funniest ones I will read off anonymously to the class. The classic one, the one that everyone uses the most to try to remember this, is "Oh, be a fine girl, kiss me." And if you use that one, you will not get credit for this exam. Okay? You got to write your own. Some of the funnier ones, and I'll read, like I said, some of the funnier ones out anonymously to the class. Some of the funniest ones that I've had previous students write are, what was it? "Only big-assed farm girls keep mules," or something like that. And then one that one of the other professors told me that one of their students wrote is, "Only brave, assertive Ferengi give Klingons massages." If you're a Star Trek nerd. I hate Star Trek, but, In any case, that concludes our lecture on Chapter 10 and stars, their properties, and how they fit into the Hertzsprung-Russell diagram, the HR diagram. If you have questions before our next lecture, of course, you can get a hold of me through the normal channels, and I hope you have enjoyed this lecture as much as I have enjoyed giving it. I'll see you next time.